Anytime we have a square matrix, let's say we have an n by n matrix, then this matrix defines a transformation or a function from Rn into Rn. Here we have Rn, and here we have Rn. And something that we can check is that if we take a vector, this vector is either going to go to the zero vector or it is going to go to another vector, which is the vector t of a of b, which is a times b. Moreover, we have that if we have a line in the domain, this line will go either to a line or it will go to the point 0. Then we're going to say that v is an eigenvector of A if, first of all, v is not the zero vector and AV is just a multiple of v. Notice that this lambda is a number, and this number can be 0. In that case, the whole line generated by v will go to just the point 0. Or, in general, if v is an eigenvector, then the whole line will go to the same line. Then this is the notion of eigenvector. And anytime we have an eigenvector, this lambda is called an eigenvalue. Lambda is an eigenvalue of A if for some vector v different from the zero vector, we have that AV equal to lambda v. Then in this video we will explain how to compute the eigenvalues and the eigenvectors, and we will go a little deeper and we will explain the notion of eigen space. Even though it looks like we need to find first the eigenvectors to compute eigenvalues, we usually find first the eigenvalues and then the eigenvectors. Before doing the procedure to find the eigenvalues, let me point out that if we have the identity matrix In, which is the matrix that has a 1 here and 1 in the diagonal and zeros everywhere else, right? These are zeros. Then if we multiply the identity matrix with a vector, then we just get the same vector. For that reason, we can always change v with the identity times v. Let's suppose that we have an eigenvalue of a matrix. If we have an eigenvalue of a matrix, then that means that for some vector v which is not 0, we have that this is equal to lambda times v. But because of this observation, we have that lambda v can be written as lambda times In times v. And if we move to the left, we get that A times b minus lambda times the identity matrix times v is equal to the 0 vector, and then we can factor the matrix A minus lambda I, and then times the vector v equals 0. But this means that when we think about the null of the matrix A minus lambda In, this null is different from the 0 vector, because we have this vector v, which is a non-zero vector and is part of the null. Remember that to be part of the null of a matrix, it means that when you multiply that matrix by the vector, you get the 0 vector. And we have seen that this is equivalent to have that the determinant of A minus lambda I should be 0. That means that A minus lambda In must be a singular matrix. Then this is the theorem. If we want to find an eigenvalue for a matrix A, then we must search for a lambda such that the matrix A minus lambda times the identity is a singular matrix. But that is equivalent to say that the determinant of A minus lambda times the identity is equal to 0. Then that's the notion of eigenvalues of a matrix. And also, once we have an eigenvalue, we're going to call this space, the null space, we're going to call it the eigen space. Eigen space associated with lambda. Right? Then this is the eigen space. This null space is the eigen space. Let's do some examples. Before I erase this, let me point out that this polynomial, determinant of A minus lambda times the identity, when we think that lambda is a variable, then when we do the computation, we get that this is a polynomial of degree n, where n is the dimension of the matrix. The matrix A is an n by n matrix. Then we can do this computation and we get that this is a polynomial of degree n. This is called the characteristic polynomial. Okay, let's do an example. Let's suppose we have the matrix A equal to 1, 4, 2, 3. And then in order to compute the eigenvalues, we need to find a lambda such that the matrix A minus lambda times the identity is a singular, but this is equivalent to find a lambda such that this determinant is equal to 0. For that reason, we need to compute this determinant. If we do A minus lambda times the identity, this is 1, 4, 2, 3 minus lambda times 1, 0, 0, 1. Then this is the matrix 1 minus lambda, 4, 2, 3 minus lambda. And then since we want this matrix to be singular so that we can find a V such that A times V is lambda times V, then we want this determinant, we want the determinant of this matrix to be 0. But then the determinant of A minus lambda I, which by the way is called the characteristic polynomial, characteristic polynomial of this matrix A, then this is going to be equal to 1 minus lambda times 3 minus lambda minus 8, which is 3 minus lambda minus 3 lambda plus lambda square minus 8. Then this is equal to lambda square minus 4 lambda, and here we have 3 minus 8 is negative 5. Remember that this polynomial that we are computing is called the characteristic polynomial. Characteristic polynomial of the matrix A, where this is A. And here is a good idea to have a checkpoint. We are always going to have that the coefficient of lambda squared is going to be 1. That always happens. the constant coefficient, this negative 5, should be equal to the determinant of A. Let's see, the determinant of A is equal to 3 minus 8, which is negative 5. Then this constant coefficient should be equal to negative 5. And this number, negative 4, which is the coefficient of lambda, this must be equal to negative the trace of A. By the way, the trace of A, the trace of a matrix, it is just the sum of the entries in the diagonal. In this case, remember that we usually refer to the diagonal, to this diagonal that goes from the top left to the bottom right. Then in this case, the trace is going to be equal to, this trace is going to be 1 plus 3 is 4. But then here we have a negative 4 because this is equal to, this coefficient must be negative the trace. Once we have the characteristic polynomial, in order to find the eigenvalues, we need to find those values of lambda that makes the characteristic polynomial equal to 0. Then let me write here, finding the eigenvalues. Then to find the eigenvalues, we need to solve the equation lambda squared minus 4 lambda minus 5 equals 0. And if we can factor this polynomial, let's see if we can factor it. That will be easier. Then it's lambda minus lambda plus, and here we have 5 and 1 equals 0. That means that lambda minus 5 should be 0, lambda plus 1 should be 0, and then lambda equal 5, and lambda equal to negative 1. Then we have two eigenvalues. An observation is that we cannot have more than two eigenvalues because the eigenvalues are a solution of a quadratic equation. In general, if you have a polynomial of order n, the maximum number of roots, that means the maximum number of values of lambda that makes that polynomial equal to 0, is going to be n. For that reason, if you have a square matrix n by n, you can have, the most you can have is n eigenvalues, or you can have less eigenvalues, but the most you can have is n. Let's compute the eigenspaces. Remember that the eigenspaces is just the null of a matrix, and we already know how to compute the null of a matrix. And we compute the eigenspaces associated with the eigenvalues. Then we write for lambda equal 5. For lambda equal 5, we have that the eigenspace, let's call it like lambda, let's call this eigenspace, let's call it eigenspace associated with lambda. In this case, the eigenspace associated with 5 is just going to be the null of the matrix A, which is 1, 4, 2, 3, minus the matrix lambda times the identity, which is 5, 0, 0, 5. At the end, you end up with the matrix that you get when you subtract from the main diagonal, you subtract the lambda. Then 1 minus 5, 4, 2, 3 minus 5. And this is just the null of negative 4, 4, 2, negative 2. And let's do row reduction. If we do row reduction to negative 4, 4, 2, negative 2, we will end up with the matrix negative 1, 1, 0, 0. This is the reduced echelon form. Then the null of this matrix is equal to the null of this matrix. But remember that the null of a matrix is the solution of a homogeneous system. What system is this in this case? Negative x1 plus x2 equals 0, a homogeneous system. Then in this case we say that x2 is free, and then we solve for x1 in terms of x2, we get this, and therefore the solution is going to be the set x2, x2, such that x2 is a number. This is what we call the eigenspace associated with this eigenvalue 5. Notice that if we're talking about the real numbers, this is a line, and in this case the generator vector is the vector 1, 1. This, by the way, this 1, 1 is an eigenvector associated with this eigenvalue lambda equal 5. Let's compute the other eigenspace. Now we say for lambda equal -1. For lambda equal -1. Then we need to compute the null of the matrix A minus -1 times the identity, and then we end up computing the null of the matrix 1 minus -1, 4, 2, 3 minus -1, which is the null of the matrix 2, 4, 2, 4. And then the null of the matrix 2, 4, 2, 4 is the same as the null of the matrix 1, 2, 0, 0. This is the reduced echelon form. And remember that the null of a matrix is the solution of a homogeneous system. Then we write the homogeneous system associated with this, which is x1 plus 2x2 equals 0. x2 is free, and then the solution would be x1 equal -x2, and for that reason the solution is going to be the set -2 x2 x2, such that x2 is a number. Let's suppose that we're working in the real numbers, and then this is a line, and a generator vector for that line is the vector -2, 1, and this vector is an eigenvector. Then we have finished our goal. We start with a matrix, we compute the eigenvalues, and we compute the eigenspaces. This is the eigenspace associated with the eigenvalue -1. And once we have the eigenspaces, we can compute eigenvectors. They are just one example of those eigenvectors are the generators of the line or the plane or the space that we get from the null. To compute the eigenspaces, we have to compute the null of a matrix, which we already know how to do. To compute the eigenvalues, we need to compute the characteristic polynomial, and then the challenging part may be to compute the solution of the equation characteristic polynomial equal to 0. But we're going to get some help from the computer to factor the polynomials. Let's do another example. Let's consider the matrix A equal to 0, 3, -2, 2, -1, 0, 4, 4, -7. Then the goal is to compute the eigenvalues, eigenspaces, and eigenvectors. To compute the eigenvalues, we need to compute first the characteristic polynomial, and then we need to solve the equation characteristic polynomial equal to 0, and that gives us the eigenvalues. To compute the eigenspaces, we compute as many eigenspaces as eigenvalues, but then essentially we need to compute the null of a matrix. What matrix? A minus lambda I times the identity, where this lambda I is one of the solutions here. And once we have the eigenspaces, we can find the eigenvectors. If this eigenspace is a line, then it's going to be a generator of that line. If it is a plane, then it's going to be the generator of that plane. And we usually count as many eigenvectors as the number of free variables that we get here. Let's start by computing the characteristic polynomial. Then to compute the characteristic polynomial, we need to compute the determinant of the matrix A minus lambda I, which is essentially the determinant of the matrix that we get when we subtract lambda in the main diagonal. Then we have 0 minus lambda, which is negative lambda, 3, negative 2, 2, negative 1 minus lambda, 0, 4, 4, negative 7 minus lambda. And then we have to compute this determinant. Remember that to compute a determinant, we need to select either a row or a column, and we usually select the row that has the most amount of zeros. Let's select row number 2. Then this is, let me remember the signs, positive, negative, positive, negative, positive, negative, positive, negative, positive. If I'm going to pick row number 2, this 2 goes with a negative, then it's negative 2 times the determinant of the matrix 3, negative 2, 4, negative 7 minus lambda, plus, right, negative 1 minus lambda, times the determinant of the matrix negative lambda, negative 2, 4, minus 7 minus lambda, and then plus 0, but I don't write that plus 0. Let's keep going. This is just negative 2 times negative 21 minus 3 lambda, this times this, minus negative 8, which will be plus 8, and then plus negative 1 minus lambda times, here we have this times this is 7 lambda plus lambda square, and again plus 8. Then what do we get? We get a positive 42 plus 6 lambda plus minus 16 minus 7 lambda minus lambda square minus 8 minus 7 lambda square minus lambda cube minus 8 lambda. We have a negative lambda cube here, and we have lambda square. We have a lambda square here, another lambda square here. Do we have more lambda square? No. Minus 8 lambda square. What about lambdas? We have a lambda here. 6 minus 7 is negative 1. Minus 8 is minus 9 lambda. And then the constant coefficient 42 minus 24 would be minus 18. Sorry, positive 18. Then this is the characteristic polynomial. And then we need to solve the equation characteristic polynomial equal to 0. To factor this polynomial, we're going to use an online website which is called Planet Calc. And then when we enter this polynomial, we get that this polynomial can be factored as lambda plus 6, lambda plus 3, and negative lambda plus 1. And this means that lambda is either negative 6, or lambda is negative 3, or lambda is equal to 1. Then we have the eigenvalues. This is the first task. Now let's compute the eigenspaces. To compute the eigenspaces, we need to do that for each eigenvalue. Then when we think about lambda equal 1, let me just say for lambda equal 1, then we need to compute the eigenspace associated with 1, which is just the null space of the matrix A minus 1 times the identity. That means 0 minus 1 is negative 1, 3, negative 2, 2, negative 2, 0, 4, 4, and negative 7 minus 1 is negative 8. Then we have that the null of this matrix is the null of the matrix 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0. And the null of this matrix is the solution of the homogeneous system x1 minus x3 equals 0, x2 minus x3 equals 0. And then for this system, we have that x3 is free. And then we need to solve for the basic in terms of the free variables. And then we write the solution as x3, 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 such that x3 is a number. This is the eigenspace associated with the eigenvalue 1, the solution of this homogeneous system, which is because it is the null of a matrix. An eigenspace is the null of a matrix, and it looks like this. But an eigenvector that we can easily pick here is the generator of this line. Here we have a line, then the generator would be this vector 1, 1, 1. This is an eigenvector, an example of the infinitely many eigenvectors that we have. This is for lambda equal 1. We can pick the other lambdas. Let's do that. Then for lambda equal negative 3. For lambda equal negative 3, to compute the eigenspace, this eigenspace, we need to compute the null of the matrix A minus negative 3 times the identity. Then we have 0 minus negative 3 is 3. Then here we have 3, negative 2, 2. These are the entries that changes. Negative 1 minus negative 3 is 2, 0, 4, 4, and here is negative 7 minus negative 3 will be negative 4. We have that the null of this matrix is the null of the matrix 1, 1, 0, 0, 0, 1, 0, 0, 0. But the null of this matrix is the solution of the system x1 plus x2 equals 0, x3 equals 0. Here, the basic variables are x1 and x3, and the free variable is x2. Then we solve for the basic in terms of the free, and then we get that x1 is equal to negative x2, and x3 equals 0. Remember that when we write the solution, we need to write it as a vector in R3 because there are 3 variables. That vector is negative x2. x2 is free, then you just write x2, and x3 is 0, such that x2 is a number. This is the Eigen Space. This is the Eigen Space. Eigen Space associated with lambda equal negative 3. And an eigenvector is going to be the vector negative 1, 1, 0, which is the generator of this line, if you are thinking that our numbers are the real numbers. Finally, let's compute the last eigenspace. Then for lambda equal to negative 6. Erase this part. For lambda equal negative 6. Then the eigenspace associated with this eigenvalue is going to be the null of the matrix 0 minus negative 6 is 6. This doesn't change. 3, negative 2, 2. This changes because it's in the diagonal. Negative 1 minus negative 6 is positive 5, 0, 4, 4. Negative 7 minus negative 6 is negative 1. And this is the same as the null of the matrix. I'm finding here the reduced echelon form. 1, 0, negative 5, 12, and 0, 1, 1, 6, and 0, 0, 0. By the way, I'm finding the reduced echelon form once again using the website Planet Calc. Then the null of this matrix is the solution of this homogeneous system. x1 minus 5, 12 of x3 equals 0. x2 plus 1, 6 of x3 equals 0. Here x1 and x2 are basic, while x3 is free. Then we need to solve for the free in terms of the basic. We have that x1 is 5, 12 of x3, and x2 is negative 1, 6 of x3, and therefore this null space is going to be equal to x1 is 5, 12 of x3. Here x2 is negative 1, 6 of x3, and since x3 is free, then we just write here x3, such that x3 is a number. And an eigenvector in this case is the generator of this line, and is the vector 5, 12, negative 1, 6, and 1. Notice that if you have an eigenvector, any multiple of that eigenvector is also an eigenvector. Then if you don't like this vector to be an eigenvector, you could have chosen the eigenvector right here. The eigenvector, let's multiply everything by 12. You get 5, negative 2, and 12. This would be also an eigenvector. Okay, let's stop here.